Okay, it's me again. So the first two lectures, so anyway, this is the third in a sequence of lectures that I've given here. Again, I want to thank the organizers. This has been a really wonderful meeting. And the first two lectures were tutorials, right? So those were not so much about necessarily our work, but about trying to overview certain things from the literature, certain things about the integration of electronics, certain things about what I thought were alternative facts propagating in the 2D literature. Today is actually a typical research talk that I would give for 45 minutes at a conference or something like that. So this is really about our research, every single thing that I'll be showing in here. So digging a little bit into the motivations of our research, sometimes I like to show this picture. This is a picture of an egg cooking on a processor. So I took this, actually I found this picture on the internet in 2005. 2005 is coincidentally also when I finished my PhD. But there's, what's interesting about this is that some computer game player, right, took the heatsink off the CPU, put an aluminum tray down, and then put an egg inside the aluminum tray, continued to play video games, and the egg was cooked, right, in a few minutes. So it illustrates that even back in 2005, CPUs were getting very, very hot. In fact, I have data to show you that. So if you look at the power density in CPUs, central processing units, notice this is a log scale. So this has gone up exponentially over the previous, decade or two. And in 2005, we had this thing called the Pentium 4, which was hitting over 100 watts per square centimeter. And since then, we've pretty much been limited by heat inside processors. So this is just a really kind of fun illustration of that, right? We've been living in this time period that's limited by heat since 2005, just like we've been living in Messi and Ronaldo's world since about 2005 as well. So those two are unrelated, by the way, as far as I can tell. So, this is interesting, obviously at the CPU level, but at this data center level, I think is interesting to look. There's a fellow at Stanford named Jonathan Koomey who puts together, every few years, he puts together the power used by data centers. Data centers are, of course, the largest electronics users of power. And he showed that between 2000 and 2011, the data center power use in the U.S. essentially doubled every 5 years. It's almost like they have their own Moore's law of power use. And notice that half of that is actually used for cooling, right? So it's not even used for moving data bits around. It's actually used just for keeping the things cool. I have seen more recent data, although it's a little bit hard to interpret, and this is actually flattening out. It's flattening out partly because people have gotten a little bit smarter at making data centers, partly because data centers are located in places like Iceland, so they have to do less cooling, right? Or Finland or something like that. So anyway, worldwide, the power consumption for data centers at the same time was about 30 gigawatts, so that's a large number as well. So, I don't work on gigawatts, but I looked it up. 1 gigawatt is the power production of a nuclear power plant, and 12 gigawatts is the power usage of the country of Argentina. According to some numbers I found online. So that's about comparable to what the data centers in the U.S. were using alone back in 2015 maybe, something like that. So that's kind of my motivation. I think, that's the mindset with which we approach research, including research on 2D materials. So in my group, we actually work on 3 different areas, which are all essentially motivated by energy, thermal issues, and electronics issues. One of them, of course, is why we're here, which is the computing and sensing with 2D materials. That's the topic of today's talk. And right now, probably 2/3 of my group works on this area. Obviously, it's grown a lot in my group as it has in the world, and you know that. But we also have projects which are unrelated to 2D materials. This actually happens to be related to thermoelectrics and carbon nanotubes. So here we're motivated by harvesting, thermal energy from the human body. I will not be talking about today, although there's a little bit of thermoelectrics in my talk on some other topics. And then we're also interested in energy-efficient data storage. If you remember my talk from 2 days ago, data storage is really, really important for enabling future energy-efficient, computing systems. And so, obviously, the more data storage becomes important on chip, the more it is important to be able to do that with very low power per function, per bit, per whatever. So I'm not going to talk about our work on phase change memory today. I think I just have one slide applying something to that. Okay, this slide I've already seen, but I'll repeat it just in case you missed, again, my lecture 2 days ago. So maybe just about 3 or 4 slides from here are repeated from my previous talk, so hopefully that will not put you to sleep. But I think this is important that it sort of fits in my discussion here. This is this discussion about Moore's Law, and how Moore's Law, essentially, in my opinion, is not necessarily dead or dying. It's probably going to go 3D. And if we read the original Moore's paper, he didn't actually say much about transistors themselves. That was done by Bob Dennard. But Moore basically talked about complexity and cost. Moore's original paper is basically an economics paper, right? He said, look, I think as long as possible, I foresee a trend of increasing the complexity of integrated circuits while finding the appropriate, sort of cost point, if the appropriate cost point can be found, right? Dennard, of course, was the IBM researcher. I think he still works at IBM, actually. Dennard was the IBM researcher who basically said, look, if you want to take a 1970s transistor, this was written in 1974, if you want to take a 1970s transistor and you want to make it small down to atomic scale, you have to shrink it in these different dimensions, right? And actually, some people have said that Dennard's law / Moore's law already ended about 2005. That's because then is when the dimensions were not shrinking as much. We started doing what's called equivalent scaling by introducing high-K materials, introducing strain, and then introducing FinFETs. But I think there's general agreement that this will end at the atomic scale. I think nobody is disagreeing with that. Okay, so a version of the slide was also shown 2 days ago. This is just very simple. What is the problem of computing today is that we have, computing chips and memory chips that are essentially separated, including in my laptop, including in your cell phones. They're typically separated, right? And so this leads to significant bottlenecks and significant energy waste while the CPU waits from data from the memory. And memory here can mean, the DRAM, which is obviously a separate chip. It could also mean the hard drive, which these days is flash. It's also separate. It's an entirely separate chip sitting somewhere else, right? So it takes a long time to basically retrieve data from memory, and when you do, data-abundant computing, this is actually really becoming this is the real bottleneck, not necessarily having smaller transistors. In the future, I think the only obvious direction to go is doing 3D integrated logic and memory, and as I said 2 days ago, my colleagues have shown mathematically that this should lead up to about 1,000 times energy efficiency in computing, right? So if you think about Moore's law today, there's, at least theoretically, we could actually do 1,000 times better, in terms of, processing data. So that's pretty impressive, I think. Of course, this is not saying anything about cost. I don't know if the cost will work out, but I think it's safe to say that at least as much as possible, Moore's law will probably go 3D. We'll see if the cost will hold up, meaning whether you and I as consumers want to pay for it, right? Okay, this is basically a better picture of what I showed earlier, a little bit more detailed. This is just my argument that this 3D heterogeneous integration is driving a lot of the two-dimensional materials work at Stanford, at least in my group, a few of my collaborators, and so on. I circled some of the places where this would fit, 2D transistors fit in there. There's thermal storage or thermal dissipation, which are based on 2D materials I'll show later. And here are the primary collaborators that I have in 2D at Stanford. So some of the work in here is obviously in collaboration with them. But I think I also said, and I said this 2 days ago, that we're definitely not the first people to really think about 3D electronics. The memory people have been doing 3D flash memory since about 2007, so more than a decade. And right now, the flash memory that is stored in your solid-state drives, in my laptop, in your phones, they're almost surely this kind of vertical flash right now. This is a cross-section of 32-layer vertical flash. I believe that's Samsung. And now they're going to 96 layers. And so the memory people have been doing this for a while. And then, I sort of like to joke that the real estate people have been doing 3D integration for a while. If you go to any big city, right, there's tall buildings which are actually significantly more energy efficient than the standalone buildings because there's shared infrastructure. Okay, So one of the questions that sometimes I get when I give these talks is, especially from industry actually, is well, how can you do this as an academic? This is very difficult. You should probably be focusing on more academic things, and of course we are. But we also like to build prototypes, and this is, I apologize a little bit, this is a very Stanford-centric slide. Because I happen to be familiar with the Stanford work because I work there, but this is the carbon nanotube computer that was put together by Mitra and Wong and Schulaker back. It's been 6 years now. It was a very simple computer, but as obviously industry would not build something like this. But for an academic group to show a proof of concept, I think it's important to show that, look, we can build more than individual devices using relatively rudimentary academic facilities. And this is something else that the same team built a few years later. This is basically a sensing system, which had sensors on top. It had memory in the middle to store the information. It had carbon nanotubes as some logic in there. And I think, if I remember correctly, it had even silicon chip as a substrate. And this was all done at low temperature, which I think I've argued 2 days ago that is important to be able to build this at low temperature so you don't damage some of the internal components. And then some work from my group, which I know I showed as well. This is us looking essentially at 4-inch wafer scale graphene circuits. Very simple circuits, but again, we did it because I had a student, Ning Wang, who was very interested in basically going beyond what some of the other students were doing, and he wanted to work with fairly average devices, but he wanted to make a small system that actually did something, somewhat useful, and in this case, it's a vector dot product that is done with using graphene. Okay, so I know I showed a version of this slide as well, because I've shown the little Hamlet character wondering whether something's 2D or not 2D. What I want to remind this audience today is that, yes, most of the talk will be focused on these 1 to 3 atom thick materials, which to me, monolayers, of course, are specifically 2D materials. And part of the reason why we focus on them is because, as you'll see in a moment, that's what we get from growth. We get monolayers, and it is what it is. But the last bullet here is actually a little bit maybe more important, is that these out-of-plane van der Waals bonds that 2D materials have with the environment actually enable heterogeneous integration without lattice matching. And we can do that at room temperature, or sorry, at low temperature. Well, at room temperature, you can do it by exfoliation, obviously. But it's very clear that you don't need lattice match substrates to grow or to transfer these things, unlike in 3-5 type materials where you need to lattice match, and otherwise you have crazy strain and whatnot. So we'll see some, obviously this is a big pro. There's also some cons related to the van der Waals bonds, actually, I'm sorry. And we'll get to those later. The other question that sometimes I get from my industry friends is, or I used to get, maybe less so these days, isn't this weird field where you just work with Scotch tape and nothing's going to come out of it because this is not scalable? And yes, true. 10 years ago we were working with random pieces of Scotch tape and random pieces of 2D materials, but I essentially banned Scotch tape in my lab. We no longer buy it. And so right now we grow everything. We try to grow everything. There's a couple of examples I'll show where we still use Scotch tape, because if you want to test something pretty unusual, as Professor Velasco showed this morning, something very clever or something very new, and you can't grow it in that configuration, it's still important to obviously peel and stick things. But this is basically CVD and CVT, chemical vapor transport growth, that my group is doing, and then in collaboration with Ian Fisher in physics at Stanford are doing. Some of the materials. This is actually my lab. This is, if you come and visit us, which I really hope you will, and if, I will give you a lab tour, and this is what our 2D materials growth lab looks like that we set up when we moved to Stanford. We have 2-inch CVD for boron nitride, 2-inch CVD for moly and tungsten selenide and sulfides, and then we have a 4-inch CVD system for graphene, which is actually in a different room, so it's not in this picture, but these are the 2-inch systems. That's the selenide system, that's the boron nitride system. So that's pretty much all the materials that you'll see in this talk, almost all of them, come from those little tubes right now, for better or for worse, with whatever limitations there are, of course. Okay, so I'll say just a couple of words about graphene. Graphene is, in my opinion, this is the closest we push to systems, right? As I mentioned earlier, the graphene 4-inch wafer scale demonstration that we had. The other materials we've mostly pushed towards devices at this point. And as an electrical engineer, you can imagine that I teach transistors classes, but it's also a big part of our research. It's a big driver, right? Transistors. They're not necessarily maybe the most important thing by themselves, but it's certainly a driver for what we do. And I think I showed a version of this slide also 2 days ago. And what I was arguing then, which I hope you still agree with, is that 20th century transistors are literally carved out of a rock, right? Silicon is a rock. It's the second most abundant element in the Earth's crust after oxygen. But oxygen doesn't make a very good semiconductor, so Intel is using mostly silicon with oxygen as for the insulators, right? But the problem is when you scale these things down, and these are beautiful images. This is some earlier work done by Uchida and Takagi, I think when they were still at Toshiba, showing transport in very, very thin silicon channels. This is like trying to make silicon 2D effectively, right? Before there was silicene or whatever, silicane. This is a 2.4 nanometer thin silicon film. But look at this. This is the 14 nanometer Intel FinFET. This is a cross section of the FinFET transistors in my laptop right now. This laptop is 1 year old, so it has these things inside of them. And you see that this thing is 8 nanometers wide. These are little fins of silicon coming out of the wafer. Current flows in and out of the plane. You see every single atom in there, which is mind-boggling. It's very, very cool. To the fact that this is actually commercial and we can buy it, right? And there's billions of these on the chip. And this is my really, clumsy attempt at putting electron scattering events on that picture, right? So an electron will, as it travels through here, in and out of plane, will scatter on the rough surface between the silicon and the hafnium oxide or whatever the dielectric is on top of it. These days it's mostly hafnium oxide, maybe with some nitrogen tossed in. So some sort of hafnium oxynitride, I think they call it. So, a possible solution to this surface roughness problem is what I call these 21st century atomically thin materials. Carbon nanotubes, of course, are part of that. And then the 2D semiconductors, the transitional metal dichalcogenides, are part of that as well. These are naturally thin materials such that the mobility of these materials, when you thin them down, doesn't actually get worse. For silicon, the mobility gets much, much worse as you thin them down below about 4 nanometers. So there's pretty general agreement in industry that nobody's going to thin silicon down below 4 nanometers. Not in FinFETs, not in silicon on insulator, nothing. Because the mobility just gets way too worse. And what I'm not really showing you here, but maybe hinting at, is that the variability will also get worse. Because you're dealing with 12-inch wafers of the stuff. And some people are talking about moving to what's next, I think 16-inch or something like that. So the variability is probably going to be untenable with silicon. But then, you have these 2D materials and 1D materials, which, within a very thin material, they have good mobility, decent mobility, not great, but decent, good enough, maybe. And they have band gaps ranging from, 0, of course, in graphene, to less than 1 eV for nanotubes, and, around 2 eV for the TM, right? So those are useful band gaps for turning transistors on and off, presumably. Okay. I promised you a couple of words about our work in graphene. This is actually old work. This is probably the only slide I have that is, almost 10 years old. This is when we started working on graphene 10 years ago, when I was still working at University of Illinois, Urbana-Champaign. And at the time, being transistor people, mostly, we decided that one of the things that was missing in the literature was the saturation velocity, right? So if you're familiar with drift, which I'm sure you all are, drift velocity of electrons or holes in a semiconductor, if you go to high enough fields, the drift velocity doesn't go to infinity, it just saturates at something called the saturation velocity, which in silicon is about 10 to the 7 centimeters per second, right? This has been very well known actually in silicon since the 1950s. That's when the first measurements were done, we found out when we were digging through the literature. Germanium measured a little bit later, but about, same decade, I think. So we wanted to measure this in graphene, and we realized that, this is actually a lot easier said than done. But we set up the measurement eventually. We measured the saturation velocity in graphene, and we realized that it's a funny thing. The saturation velocity in graphene actually is a function of carrier density. It scales as 1 over the square root of carrier density because of the weird graphene dispersion relation, right? Which is not parabolic like silicon. It's this funny Dirac cone that you all know. And this is what the population of forward moving and backward moving electronic states, or whole states, because it's the same thing really, look like in graphene. But the good news is that these numbers are bigger than the saturation velocity in silicon. So if you want to make good high-speed transistors where you don't care about turning them off, this is good news. Mostly good news. We have a habit of also creating compact models. By the way, to me, these are compact models. So electrical and thermal compact models. We have a habit of doing that in my group. And so you'll see that throughout the talk that we extract models as much as possible. Some of them, we try to make them as simple as possible, but still combining some of the physics, or still containing the physics in it, such that they are useful to students in my group as well as to other people in the community. So we don't have to do very, very complex simulations for certain things. This is not an unusual project. It's not an unusual result, but I use the word unusual in my title because I have a couple of other unusual ones. What's unusual here is the participant, and I'm really proud of her work. So Megan was a high school student when she came to work in David Goldhaber Gordon's group. So she was a 16-year-old high school student, came to us from a high school nearby. And David approached me and he said, he and I had been talking about redoing my old measurement that I just showed you, but redoing it in David's really, really clean boron nitride, graphene, boron nitride structures, which, these days, these are sort of state-of-the-art, mobilities of 50 to 100,000 at room temperature. And so we assigned Megan on this project and she made it work. She helped, build some of the devices. She worked with a graduate student, of course, who helped her a lot. She did all the measurements. We helped with data interpretation because, obviously a high school student, she had to pick up a lot of quantum mechanics, essentially, to be able to do this. But she put together a paper. She, obviously deserved to be first author, so very proud of that. The end result, like I said, is maybe a little bit less surprising. What would you expect if you redo the measurement that we did 9 years ago with a better boron nitride encapsulation? You're going to get a higher drift velocity in graphene, right? Saturation velocity. So the saturation velocity is 6 times 10 to the 7, which is about 6 times that of silicon. You can see this is the raw data right there. It still scales as 1 over the square root of the carrier density because of the physics in graphene that I described earlier, but it's significantly higher than silicon. And as far as I know, this is actually the highest drift velocity recorded in a solid. The next highest belongs to indium antimonide, which is about half what it is in graphene. So that's kind of interesting. I mentioned modeling work in my group, and some of the models that we've developed, again, when we have time and when the students are inclined, we put them on this website called the NanoHub, nanohub.org. And this is a graphene simulator tool that we put online. So you can go in there and just has some default parameters which are consistent with devices from our lab. And then more recently, we've posted a semiconductor simulation tool, 2D semiconductor simulation tool, which is really aimed at more circuit design. So this is more of a device kind of tool, and this is more of a circuit tool, but it has the physics of a 2D semiconductor. And if you change the parameters, you can pretend it's MOS2 or you can pretend it's WSE2. You can change the contact resistance, all of those things, and you can plug it into a circuit simulator. And these, by the way, are also linked from my website, so you don't have to necessarily go search from them there, but they're directly linked from our website. Okay, so a couple of words about the growth of 2D semiconductors. Remember I told you that we do this in our lab. I showed you our lab. But I also said that mostly we get monolayers, right, when we do the growths. And that's good, I suppose. I mean, I would love to get a pure bilayer as well, but we don't know how to do that today. And so right now we grow these things in this 2-inch tube furnace that I showed earlier. The growth temperatures recently we've been able to reduce down to 550 Celsius. 550 Celsius is good because if you remember my talk from 2 days ago, I was arguing that industry really wants us to be below 500 to take this more seriously, right? And so we're trying. I'm not sure if this is actually the right way to do it. Maybe ALD growth is better, but this is what we have currently available, and so it is what it is. This is a full a full wafer. No, it's a full kind of like a 1.5 by 2 centimeter chip, silicon oxide chip on which we grew this material. We etch away the MOS2 to create the Stanford logo here, and this is a picture taken with a cell phone camera. So I think this is kind of interesting. I mean, obviously, you know, it's mostly for fun, but the scientific value that it has is that it actually reminds us that with the naked eye, you can see the contrast between a monolayer of MOS2 and the lack of a monolayer of MOS2. So there's actually significant absorption happening in there. So, you know, that's interesting. The growths, by the way, we can do, these are Van der Waals growths, as I mentioned earlier. We can do them on anything that we can stick in the furnace, right? Smooth enough, presumably. So we can do it on SiO2, quartz, silicon, aluminum nitride, amorphous aluminum oxide, and sapphire. We've done it on all those substrates. It works. And we're happy to share samples if you like some of those substrates, or if you have some other substrate in mind, we can try the growth. In the middle of the chip, it looks boring. Good boring, right? This is a good kind of boring. You don't see any features. You don't see, you know, really anything in there. But if you, sorry about a little bit too happy there with the button, but if you look at the edges of the chip, I'll be honest with you, our growths are not continuous. However, you can still see the size of the growths, right? You can see the size of the grains, I'm sorry. They're about 50 to 100 microns for these growths. And then because we were doing this work in an election year, this work was done in the summer of 2016, and, you know, we were bombarded everywhere by, you know, Trump, Clinton, Trump, Clinton, Trump, Clinton. We also went and we etched, by e-beam lithography, we etched the little presidential candidate faces into the MOS2. We know how that ended, that election. And so later on, somebody told me that it would be nice to have Nano Trump to say something like he says things, right? So he says, make MOS2 great again. Okay. On a more serious note, you will see that the nano presidents or nano presidential candidates, they have dots on their face, right? And so those dots actually really worried me when I first saw these pictures. And I realized that actually our growths are not as uniform as I wanted them to be. Those are bilayer regions, by the way. So mostly we get 90% monolayers, but we get 10% bilayers. And we don't have extremely good control with these CVD growths. And so, by the way, of course, you know, working with a TM collaborator, you know, if you pick the right region, it looks beautiful, right? But it doesn't look like that everywhere, right? So there's regions, of course, where it looks like this, and it's nice and whatnot. But if you zoom and look somewhere else, you'll see the polymer residue and all kinds of other stuff. So, and defects and so on. So I wanted to study, like I told you, I was worried about the bilayer regions. Like, I really genuinely was worried about them. So I told my student, this is Kirby Smith, who was a very, very prolific, very hardworking student. I said, hey, you know, do you think you can study the variability of these devices, right? And he said, okay, I'll make hundreds of these transistors. So he made hundreds of these transistors because now he has a large area chip to work with, right? This is very difficult to do with exfoliated stuff, right? So this is the benefit of having CVD material, even though the drawback appears to be, whoops, bilayers. But he measured all these devices, you know, kudos to him. And here he plotted all the data that he took from hundreds of devices. This is the mobility he extracted, and this is the contact resistance, right? And I'm not just showing you our best device, I'm showing you the worst device as well. I'm showing you all the devices, and so for that I need a histogram, right? And so here it is, the mobility ranges from 25 to 50. Keep in mind this is a 3-atom thick material, which is occasionally 6 atoms thick in some regions. So that's not too bad for as-grown material and SiO2. And the contacts are not doped. I'll show better results later, but they're centered around 2.5 kilomicrons, which it is what it is. So the surprise when we started analyzing this data is we realized that, wait a second, you know, for a semiconductor that is varying from being 3 atoms here and 6 atoms there and back to 3 atoms again, so it varies by 100% in regions, this is actually very low variability. This variability can be easily explained just by variation in doping, right? And so a variation in doping and maybe charge traps in the SiO2 or things like that, or maybe just defects. You know, it's definitely not the bilayer regions. In fact, we've measured transistors that actually have no bilayers, and they look exactly the same, right? So transistors that have bilayer dots and transistors that don't have bilayer dots, they look pretty much the same as far as we can tell. And so that was good news, because remember, just a minute ago, I said I was very worried about the bilayers. And there's actually some cool physics in this, because what we realized is that the conduction band offsets between monolayer and bilayer and MOS2, we get lucky. The conduction band offset has been measured, even before we did this, to be only about 55 MeV. That means that that's about 2 kT at room temperature. So that means that the electrons travel in the monolayer, and they don't care the bilayers are there. It's different for holes. Holes would actually probably prefer to get trapped in the bilayers. So probably the bilayers may actually have hole puddles or hole regions or whatever. But the monolayers, they don't really seem to care. Sorry, the electrons don't really seem to care. The holes, unfortunately, we don't have data for the holes, but that's my prediction for what would happen to holes. So good for electrons, maybe not great for holes, but we can soldier on with the electron part of MOS2 for now. Okay, once these hundreds of devices became available in my lab, a lot of other students and collaborators wanted a piece of the action. One of them was Elam Yalon, who is now a professor at the Technion in Israel. But Elam wanted to do thermometry. He really wanted to work on thermometry of nanostructures, memory devices, MOS2 devices. And so he read up on, he had no background in Raman, by the way, so he read a lot of the Raman papers, actually from the previous speaker and from others in literature, and as well as the Raman papers on thermometry, specifically of 2D materials that were there before us. And eventually, he was able to measure the temperature of a functioning MOS2 device, including those bilayer regions. You see the dots in there. I mean, this device is not necessarily uniform either. So he also didn't see any hot spots or cold spots where the bilayers are, so he confirmed that the bilayers kind of don't matter. Again, kind of good news, I guess, right? But then the bad news, I suppose, was that as these transistors operate at pretty high current, they get hot. And so we very quickly realized that not just our data, but also all the other data that had been published in the literature on high current operation of these 2D transistors was actually not at all at room temperature, or whatever the ambient is. It was actually at least 200 degrees hotter. So for us, this was meaning up here, these devices were actually becoming over 200 Celsius hot. And in fact, I don't have time to talk about it here, but in the paper, we showed how we pushed them to the breakdown temperature of MOS2, and that's correlated with what other people have actually shown that MOS2, when it's exposed to air, tends to break down at. So we were able to, we can confirm this other ways too. So the question is, why is this happening? And remember I said earlier that van der Waals bonds are great for 3D integration. They're not that great thermally, it turns out. So it turns out that if you have a monolayer, material stuck with van der Waals bonds to, whatever the substrate is, in this case SiO2, this is a very, very thermally resistive interface because it's a very weak coupling for the phonons to couple across that interface, right? And so that's actually bad news, right? And we're still struggling a little bit. We really, I would appreciate your help. I know there's a lot of thermal experts in the community here. And this is, by the way, molecular dynamics work that my student Alex Gabery is doing, trying to understand how to improve that interface thermally without messing it up electrically. And that's something that we're struggling with still. Okay. Now, different student, Chris English, was in the group around the same time. This is 3 years ago now. And he was a big electron beam lithography user. He said, I'm good at E-beam, I'm good at the Wraith system. I'm going to make a 10 nanometer scale transistor because nobody's done it in MOS2. And so he did. He put down an aluminum gate, which oxidized all the way around. There's the gold contacts. You can't see the MOS2. The MOS2, there's a monolayer right there. You can barely see the contacts, but it's hard to capture a monolayer in TEM sometimes. But it's basically this. It's really, this is the cartoon, and this is the finished device. We measure the capacitance, because we need to really understand what the capacitance of the gate is. And to make a long story short, this really looks a lot like silicon on insulator transistors that industry actually has commercialized. IBM puts all these SOI transistors based on silicon in their server chips. Except, in silicon, these are 10 nanometers thick. Here we're making them with a 3-atom thick channel, which is about 6 angstroms, right? And so that's what this is. This is the ultimately scaled SOI transistor, where S no longer stands for silicon, it just stands for semiconductor in this case. And we were able to push what at the time was a record current, 400, almost half a milliamp per micron of width through these monolayer transistors. But, still it turns out that this current was limited by heating. These devices get hot. And even before the heating starts to really hurt you, turns out the contact resistance down here, you can see there's some Schottky barrier at the contacts. So the contact resistance is not that good. Doping is not controlled, so we just have no good control for doping here. And the insulators are obviously nowhere near ideal like industry has, like really, really good hafnium oxide insulators. These are sort of academic quality, aluminum oxide, silicon oxide. So that, motivates me to tell you a little bit about our work on contacts. So the upshot of this work is that we realized that contacting 2D materials, surprise, surprise, is very difficult. You're trying to push current from a big chunk of metal into a 3-atom thick material, and that's not going to be easy, right? And one of the things that we realized is that actually if you have cleaner surfaces, you can actually get better contacts. And so we did this in sort of an average evaporator, 10 to the minus 6 torr, and we did this in a better evaporator, 10 to the minus 9 torr. And of course, in the end, I know it sounds kind of simple and simplistic in hindsight, but we realized that, hey, you need pure gold. Remember, I think even yesterday I said no titanium for these contacts. So we removed the titanium because titanium we realized was bad for MOS2. And then we put pure gold contacts, and the pure gold contacts in the better quality evaporator with a lower pressure gave us cleaner contacts, lower contact resistance. So that's good, but it's not good enough. It turns out, here's our current data, and this is probably how good we can be. This is sort of what we call the ballistic limit of the contact injection. So we can probably be, maybe this is too optimistic, but certainly we could probably make these contacts about a factor of 10 better. And now, I didn't know this at the time, but now we know that gold, for example, creates little balls. It balls up on the MOS2. So our interface is actually not perfect, which is actually why people like to use titanium to begin with. But like I said, titanium actually makes things worse for us. Okay, so how do you fix the contacts, or how do you even exert better control over these transistors? Doping. Doping is absolutely crucial for this. This technology will not move forward without really, really good, really controlled doping. And I really mean, I want to have, exactly 10 to the power 19 per cubic centimeters or whatever, like they do in silicon, right? Exactly that much doping. Or, if I choose to, I want to have no doping somewhere else, right? To create all kinds of things. And so right now, our solution to this is to put on top layers of oxides. Example, for WSE2, we've been able to dope it really, really strongly p-type using moly oxide. If you look at the paper, you'll see that there's actually a WSE2 flake underneath there, but this is just covered with crystalline moly oxide, and it turns out that crystalline moly oxide actually is a really, really good p-type dopant, and it makes this WSE2 so p-type, generally p-type, that the IV curve just looks almost flat. It's not metallic. It's still 2H phase. As far as we can tell from Raman and other things, it's just very heavily doped, so we can no longer use the backgate, just barely use the backgate to control it. But maybe just as importantly, this is a stable dopant, right? I don't know if this is the best dopant. Maybe this industry probably would not like this, but it is a pretty stable dopant for the time scales of which my students have patience to test things. So it was about the same after 20 days, at least in log scale. And so we are able to push currents nearly 1 milliamp per micron in WSE2, which I think is still the record to this day, and 800 ohm micron contacts. This is a 6-layer material, so this was actually exfoliated WSE2 because at the time we didn't have very good WSE2 growth in our group. More recently, we figured out how to make N-type doping. In this case, for MOS2. MOS2 is a little bit easier to N-type dope than the other materials. And the way we do that is, again, we cap it with aluminum oxide, but it's a funny kind of aluminum oxide. This is non-stoichiometric aluminum oxide. This is not the best quality ALD aluminum oxide we can find. This is deliberately low temperature, slightly oxygen deficient aluminum oxide. And those oxygen deficiencies, it turns out, essentially create certain charge states in the aluminum oxide which transfer electrons to the MOS2. And the MOS2 all of a sudden becomes way more N-type than it originally was. And this process, by the way, improves our contacts. So right now we have contacts to monolayer of MOS2. This is CVD grown now. Monolayer of MOS2 contacts less than half a kilo micron, which I think are pretty good. And they're very stable, by the way. And we're pushing 700 microamps per micron through these monolayers, 3-atom thick transistors, which is insane amount of current density. In fact, we looked at the real current density, megaamps per square centimeter. This is the data that we found in literature, including ours from the previous devices. And now we're up here, we're actually pushing over 100 megaamps per square centimeter through a 3-atom thick material. Most metals like copper will electromigrate and break down at about those kinds of current levels. So this is actually pretty good. It's good news, I think. Maybe not the most industrially compatible way to dope things, but I hope I've convinced you that doping is extremely important, and we really, to move this forward, we have to take it seriously. I showed the work that Megan had done on graphene velocity saturation, and so I had a different student, in my group, Kirby Smith, who also looked at drift velocity saturation, MOS2, around the same time, and basically, it's a semiconductor. We ought to look at the saturation velocity in a semiconductor, right? It's not a semiconductor with very good mobility, right? Unlike graphene, so the saturation velocity is not going to be that high. In fact, it's about a factor of 10 lower than what we found in graphene, right? And so I'm plotting here saturation velocity for a number of semiconductors as a function of band gap. And so graphene was up there. Indium nitride is up there. By the way, a lot of high-speed transistors made out of indium nitride, it turns out. Gallium phosphide, gallium nitride, pretty good. MOS2 is over there. I think I mentioned the other day that MOS2 is really, I think, competing ultimately with polysilicon and with oxide-based transistors, not necessarily with crystalline silicon, at least not with this kind of saturation velocity. But there's a silver lining to this kind of disappointing result, and that silver lining is that the saturation current could still be more than 1 milliamp per micron if we could push the carrier density reliably above. This number is actually not that scary, 2 times 10 to the 13. This is maybe more difficult. We have to remove the heating because we realized, boy, this is all limited by heating. All these IV curves, it's all limited by heating. So we can't really push the current to higher values right now, not in my lab right now. Okay. You notice that we have a habit of benchmarking things. We always say, hey, we build a transistor. How good is it compared to what? Compared to literature, compared to what silicon people think they want to be at. And so we often go back and look at this IRDS, International Roadmap for Devices and Systems. And here is what they want for contact resistance, 300 or less, mobility 150 or more. And this is what they want for current. And so it turns out, as I argued yesterday, I think, that the on current of our 3-atom thick transistor actually nearly meets the specifications, right? And the off current actually is better, right? So again, some good news. The bad news is, as I think I mentioned yesterday as well, that the contacts, the threshold voltage control, and the doping are really not that good for these devices, right? So that is a problem. More benchmarking. This is actually really just showing you the off-state current, and I may have shown this plot before. This is on and off current. So the on current for a bunch of devices, this is different materials, from black phosphorus all the way to IGZO, indium gallium zinc oxide. Notice this is band gap for the material. So the on current is, give or take, it scales with mobility, right? So, if you have good mobility and good contact resistance, you're going to get the on current that, these metrics, the low power and high performance metric require, right? And you can see that, silicon obviously meets that metric, but heck, germanium and indium gallium arsenide surely meets that metric. Indium gallium arsenide meets it very well. And MOS2 just barely maybe meets the low power metric. IGZO does not meet those metrics, but IGZO has a really, really good off-state current. Our monolayer MOS2 is the second best off-state current, and then things like, of course, BP, black phosphorus, and indium gallium arsenide simply cannot get those kinds of off-state currents because the band gap is not sufficiently large, right? And so, again, I don't have time to show the data, and actually, truly speaking, this data is actually unpublished, but we've measured off-state currents. These off-state currents we haven't published yet, but we've measured them down to very special devices, very special structures. We've measured them to be down to about 60 attoamps per micron, which, again, requires very special equipment and special devices to measure them, but ultimately, that's the fundamental limit is down here somewhere because it's going to have to scale with the larger band gap of the material. Okay. I think I showed this as well. This is more of a personal plug again, or plug for my group, rather, my students. We've put together an online benchmarking tool, 2d.stanford.edu. This is the website. You can go there right now. I hope it's working. And here we put all kinds of data from the literature that we find, current versus channel length. You can select only the monolayers. You can select only whatever material you're interested in. And I am certain that this data is very incomplete. So I would appreciate, obviously, if you send us email or just click that button right there and you say, hey, there's a really good paper that came out in 2016 and you're missing it. Please add the electrical data. Thank you. Okay. Just one more word about something a little bit unusual with a different 2D material. So that silicon, you probably already know this, I'm sure you know this, silicon is a really good semiconductor, not just because it has sort of like a decent band gap, but because it has native SiO2, right? The reason people switch from germanium to silicon is because, back in the 1950s and 60s is because silicon has a native oxide that's very good, and the germanium native oxide is bad, right? But about 10 years ago, people were no longer happy with SiO2, so they started putting, hafnium oxide or zirconium oxide in there. So my student, Michael Mletzko, who is a very creative individual, he wanted to ask the reverse question. He said, if you start with what insulator you want, can you work backwards and ask, what is the semiconductor that will give you natively that insulator? And it turns out that one answer to that question is hafnium selenide or zirconium selenide. So these two layered semiconductors, hafnium selenide and zirconium selenide, oxidize very easily, maybe too easily, into hafnium oxide and zirconium oxide respectively, right? And here's an TEM image cross-section of, obviously a thick chunk of zirconium selenide that was transferred onto silicon and capped with platinum, and before the capping happened, the top layer is already oxidized into some zirconium suboxide, right? It's very clear that it does that. This is just ambient oxidation, and that's probably just ambient oxidation too. I don't remember if my student did this in the glove box or not. Probably he didn't do it in the glove box on purpose, just because he wanted to see, more clearly how the oxide forms. But we can make transistors out of this. The transistors are not that great, so I'm not going to sit here and tell you that they're amazing, but they're interesting. I think it's an unusual thing, and this has really drawn the attention of pretty serious companies like TSMC. Their CTO 2 years ago highlighted this as an important breakthrough during 2017 in the transistor world, I guess. Again, the performance for these devices is not great. We were only able to get devices working down to 3 layers, so we've never seen a monolayer hafnium selenide device. We just don't have such good control over the oxidation. But we got them working, and mobilities are not great, but we got them working, and it's still kind of interesting. And so I call this kind of an unusual 2D thing, because it's sort of thinking a little bit differently, and also moving away from MOS2, which a lot of us are obviously in love with because it's so stable compared to that. A couple of words about thermal work in my group. Obviously, thermal work related to 2D materials, and then I'll wrap up. So I think I showed this plot yesterday or 2 days ago as well. And this is just my way of basically saying, look, here's a thermal conductivity of a bunch of materials known to us as a function of band gap, right? And there's copper, there's graphite, fine. They're metallic. They have good thermal conductivity. I'm sorry. There's boron arsenide. By the way, boron arsenide is a newly discovered material that was theoretically predicted first, but recently measured to actually have a very good thermal conductivity. The band gap is not large. It's less than 2 EV, but it's there on our plot, of course. But if you want materials which are truly great insulators, which also have large thermal conductivity, suppose that you want that, right? You have 3 options, and the 3 options are diamond, boron nitride, either cubic or hexagonal, and aluminum nitride. And diamond is not really my thing. One of my colleagues works with it. She says it's very difficult to grow, and so I already have enough problems, and so I don't want to add another one. So for now, we're focusing on the nitrides, either boron nitride or aluminum nitride, and we're particularly interested to see what we can do with this, maybe in terms of nanoscale heat spreaders, dielectrics, and maybe even trying to understand system level insights. And here's our current effort with boron nitride. We grow boron nitride in my lab. It's not great, but we occasionally get the monolayer. Monolayer is working. We occasionally get multi-layers. This I actually kind of really like, so I want to show this because I think it's cool. Here, we were approached by Applied Materials, which is a semiconductor equipment manufacturer, and they had a really wacky idea to use carbon nanotubes as a filter, a particle filter, but in their high throughput optical lithography tools, something that I've never thought about. But their nanotubes were being destroyed by the high-powered light. I don't know if it's UV or whatever it is, but they were being destroyed. And they said, can you coat carbon nanotubes with boron nitride? And I said, I doubt it, right? I mean, what are the odds? But then, since we have a boron nitride growth furnace, we took a bunch of carbon nanotubes and we stuck them in the furnace, and surprise, surprise, we actually noticed that boron nitride will grow only on the carbon nanotubes. So this is one of those things where I thought, no chance. Then the student tried it, and she got it working the first time. This is Victoria Chen's work. And so, I'm glad I didn't say I'll eat my shoe if it works, because then I would have had to eat my shoe. Now, the interface right here, the boron nitride and the carbon nanotube, we don't know how good it is, right? So she's now playing with optimizing that growth. In fact, Applied Materials hired her for the summer. I haven't seen her in 3 months because they hired her for the summer to work on this problem, actually, deep inside the corporate environment. And so I don't know what she's doing, but presumably doing good things. I'll see her when I go back next week, and I'll try to learn more about it. We've also worked with Mario Lanza, who is one of these researchers very interested in memory, and we've made boron nitride memory. This is not so special to me, because I think, I sort of joke with my students that any material that's defective can be used as memory, right? Any defective oxide, any defective boron nitride, it just means you have defects and you can kind of switch them electrically. But Mario thinks that this actually has better neuromorphic applications than other oxides for memory, because you can more gradually program those defects in our defective boron nitride. So, I'm more interested, personally, I'm more excited about the heat spreader thing, but notice sometimes, it's important to kind of look around, not just say, I'm just going to do heat spreaders, because, interesting things happen when collaborators come to you and say, hey, can you grow these on nanotubes, or can you grow these for memory applications? And I'll be honest with you, I hadn't thought about that. That was really from the collaborator, so it's really important to listen. I think I showed a version of the slide too. This is really just ordering some of the 2D materials that we know by in-plane and out-of-plane thermal conductivity. Clearly, boron nitride's up there, graphene, graphite is up there somewhere. And then out-of-plane, they all look pretty bad because you have the weak van der Waals forces, right? And this is the main take-home message for now. There's a huge thermal anisotropy of 2D materials between the in-plane and the out-of-plane thermal conductivity by factors of hundreds in some cases. And so, Alex Gabery, the student in my group, wanted to actually understand this a little bit better. And he was actually really, inspired by the work done by the transistor people in my group. And he saw that the transistor people were always complaining, hey, my transistors are getting very hot, and it's limiting their performance. In other words, these high performance, we've made 2D transistors which are sufficiently high performance that they're thermally limited. And so Alex wanted to understand, what role can the insulators play? So, first he set up this MD simulation for, suspended MOS2, not useful, obviously, as a transistor, but you got to do that first. He can break down the total thermal conductivity in plane and out of plane. This is the cartoon showing, how the different contributions are. You can do this in computation. In experiments, of course, not. But this is what I think is really more interesting to me and to the transistor folks in my group, the transistor people in my group, is when you take this suspended MOS2 and you put it on aluminum nitride, the thermal conductivity drops by a factor of, by about 20%, okay? If you put it on SiO2, the thermal conductivity drops by over 70%. That's bad news. And if you encase it with SiO2, it actually gets a little bit worse still. This is what transistors probably will look like. So that means that if at least our simulations right now, there's no experimental data, but our simulations show that if you take MOS2 and you put it on an insulator, or if you take it and you put it on, you sandwich it with an insulator, the thermal conductivity goes down a lot, right? And this is, by the way, this is known for graphene. There's data for graphene showing this, both from my group, from Li Shi's group, from a couple of other groups. So there's general agreement that this is true for graphene. There's no such data for MOS2, just these molecular dynamics simulations for now. The physics, I asked Alex, I said, Alex, just give me the straight answer. What's the physics? And he said, the physics is scattering with remote phonons. So if you look, I apologize, this is a tiny plot. If you look at the density of states for the phonons, amorphous SiO2 just happens to have a lot of phonon modes right in a regime where MOS2 likes to scatter. It also has phonon modes, lower energy phonon modes. And so these things like to couple. And so that means that the thermal conductivity of MOS2 probably will suffer on SiO2. But the good news is that on aluminum nitride, it's actually not that bad. And the other good news is that maybe this doesn't actually matter that much, because remember I argued earlier that it's really the interface resistance, the thermal interface resistance between the MOS2 and whatever the dielectric is, that actually probably matters more, especially in transistors or something like that. So some of this is ongoing work. Some of this is obviously depends on the length scale, depends on the material, but I think it's interesting to me that there's some cool physics here between what the phonons are doing to the thermal properties of MOS2 in plane versus out of plane, and there may be some opportunities for tuning this, to actually designing insulators that are actually better thermally as well as electrically, and I don't think people have only really thought about insulators from an electrical point of view. This is another study that we've recently done, speaking of out-of-plane thermal transport. This was just published about a month ago. What we did is because we can grow now all these materials in our lab, we just took them from all the growers in our lab, from all the students who do the growth, and we went to the glove box, and my postdoc, Sam Vaziri, started layering them. I said, Sam, go as much as you can. After 4 layers, he got tired, and he said, I can't do anymore. I said, okay, do the thermal measurement. Measure how heat flows across the 4 heterogeneous layers, right? The word heterogeneous here is actually important. It should be on the slide. The layers are all different. And so what we did, and this is the contribution of the second author, Elam Yalon, who's now at the Technion as a professor, he realized doing this purely with Raman heating would be actually quite difficult, because you need to know the absorption of each individual layer. And remember I told you yesterday, boy, that's going to be difficult. So what he did is he actually just used the graphene layer on top as a transparent heater. Very clever guy. So he said, let's just use the graphene. See, the top layer is always graphene. Graphene's always the top layer. And we use that as the electrical heater, because the electrical heating of graphene is very well quantified. If you put 4 probes on it and you push current through it, it's fine. And then, of course, the heat will flow downwards, and then we can still measure the individual Raman modes of the individual layers. We can figure out their thermal conductivity. In fact, here's a temperature as a function of power input for multiple layers in the stack. We can measure each layer in the stack, including the silicon substrate, which also gets a little bit warm. And then finally we ordered all of this from the worst thermal interface is graphene with WSE2. The best thermal interface is graphene with SiO2, and everything else is sort of in between. And what we realized is that the simple explanation that we have for now is that it's really the mass and phonon density mismatch between the layers that is causing this major thermal bottleneck between the layers. Major in the case of graphene WSE2, and maybe less major in the case of graphene SiO2, and then everything else sort of in between. And of course there's error bars, so I mean, there's definitely a trend, but there's also obviously a lot of error bars in our data. So I can only say as much as my error bars allow me to say. But anyway, ultimately we've demonstrated a heterogeneous material with a really large thermal resistance, and the effective thermal conductivity, if I may say so, across these 4 layers here is about 0.01 watts per meter Kelvin, which is about 2 to 3 times lower than air. So that's a very good thermal insulator. So of course, when I present that data, one of the questions I get is, okay, well, what's the electrical conductivity across the layers? We're still working on that. It turns out it's not that easy to measure, but I have a student working on it. But we've done something like that, inspired by that work. We've done it in a regime where it actually does work electrically as well. This is an application to phase change memory. This is a little bit of an unusual application because essentially what we're doing is we're taking phase change memory, which has this funny germanium antimony tellurium compound in there, very common tungsten plug, and then we stick one layer, just one layer of graphene or MOS2, either graphene or MOS2 or nothing, at that interface. And so what's unusual here is that we're using graphene as a thermal insulator. It's still electrically sufficiently conducting, and then the MOS2 is also used as a thermal insulator that is electrically conducting enough. And sure enough, you see a big difference between the control devices to the ones that had a graphene thermal insulation and the ones that had an MOS2 thermal insulation. And that's actually pretty interesting. We took out a patent on this. We said maybe industry will find this interesting. I don't know how exactly we're going to scale this, you know, at the sort of industrial level, but it certainly shows that you know, these thermal barriers can actually have a real energy impact on essentially what's a commercial technology. This phase change stuff is commercial. I mentioned the other day you can buy it on Amazon. It's not the best memory out there, but it's pretty fast and it's energy inefficient, and so this helps with the energy efficiency. By the way, here I'm plotting the thermal boundary resistance as a function of thermal conductivity. Graphene is actually not the best material to use here. Actually, MOS2 is probably better. And I bet something like tungsten telluride is probably even better. So maybe we should simply just put tellurium at that surface. Though tellurium may, well, anyway, we'll see. We'll see. There's a couple of other options. One other thing, one other technical slide, and I'm done, is we've also worked on what's called a thermal transistor. And this really came out of a discussion with the battery colleagues at Stanford. This is particularly Yi Tsui, Davide Donadio, who I know many of you know, did the simulations for this work to help us understand what the heck is going on. But the short story is that we took, this is multi-layer MOS2, and using the battery technique, we pushed lithium into it, and we pulled it out. We pushed lithium into it, and we pulled it out. And we can do this repeatably, and we can do the thermal measurement, you know, like that. And you can see that essentially I can modulate the thermal resistance of this little device by a factor of almost 10, which is pretty interesting. I mean, this is, you know, it's not a very fast thermal transistor. Notice the times are minutes, right? But I think we know how to make it faster. But the fact that I can modulate the thermal resistance of a solid material by a factor of 10 is actually kind of interesting. And so that I think has some interesting applications to control heat flow in some you know, geometries. If we could do it probably preferably faster. This is my last slide, really. Well, second to last slide. This is just to sort of give you an idea of some of the thermal measurements that we're currently doing in the group. These are hopefully all studies that will either come out very soon, well, this one just came out, or will be coming out soon. So we're using either more Raman thermometry on various kinds of crazy things when we can. Of course, Raman thermometry has a spatial resolution that's diffraction limited. So we also installed a scanning thermal microscope in our lab, which is basically an AFM tip that also does thermal measurements. And we're actually using that to measure temperature inside functioning memory devices. And here it's pretty cool because you can actually see a single filament forming inside a resistive memory device. This was a pretty boring hafnium oxide device, but you can see where the filament gets hot, and so that's kind of interesting. You can also see a single carbon nanotube heating up, which is work that Stephanie Bohajchuk in my group has been working on. Okay, so this is kind of like my forward-looking slide. This is where things are going, and I would love to have your help with these things. Driven by a lot of these applications, I think we really ought to have, obviously, high-quality growth and integration below 450. Industry always presses us on that. And then industry doesn't really know this yet, but they really should. We also need 12-inch wafer-scale boron nitride, preferably, you know, in controllable layers, right? So if you could do that, I think you'd be amazing. Those are things on growth that I really would love to be able to achieve either in my lab or with collaborations. We're struggling to determine the defects. You know, all the stuff with transistors, all these IV curves, all these contact resistance measurements, we don't know what the doping is. We don't know what the defect density is. We really don't know. We're struggling. This is a metrology challenge that we really need your help with, whether it's optical techniques or STM techniques or TEM techniques or whatever. You know, this is very important. Nobody ever got fired from Intel for saying, boss, we need higher mobility, right? So, that's sort of the most obvious bullet on here, right? Of course I want higher mobility. Preferably 150 seems to be a decent number to beat in these 2D materials, but I'll take, 15,000 if somebody gives it to me with a decent band gap. Again, nobody ever got in trouble for saying I need contact resistance, the lower the better. I want zero contact resistance, right? And I want doping, but all of this is really only achievable through doping. And I showed you that we have some ways of doing doping. I'm not convinced they're the best ways, but there are ways to do doping by moly oxide and aluminum oxide, capping layers. But they're really just academic sort of level doping studies. And so I'll stop on the acknowledgement slide, which you've seen before, so I'll be happy to take questions. Thank you.